Have you ever stopped to think about how your computer is even possible? I mean, you're streaming music, downloading a huge file, you've got a dozen browser tabs open, and it all just works. It feels like magic, right? Well, it's not magic. It's an incredibly clever dance called CPU scheduling. And today, we're going to peek behind the curtain and see how the juggler does it. So let's get right to the heart of it. The big problem is this. Your computer's processor, its CPU, can fundamentally only do one single thing at any given microsecond. So how in the world does it create this flawless illusion of doing everything at once? This is the core challenge that every operating system has to crack. You know, the secret to solving this lies in a simple fact about how programs work. A process isn't just a freight train running on the CPU at full tilt. No, its life is more like a series of sprints and rests. It'll do a burst of heavy calculation, that's a CPU burst, and then it'll spend time just waiting for you to type something or for a file to load. And those little moments of waiting, that's the golden opportunity for the CPU to jump to another task. Okay, so if the CPU has a bunch of tasks waiting, how does it choose which one to run next? Well, the most obvious answer is to just treat it like a line at the grocery store. First one in line is the first one to get served. We call it first come, first served, or FCFS. It's simple, it feels fair, and it's the most intuitive place to start. So let's run a little simulation. Imagine 3 processes pop up, all ready to go. You've got P1, this big, heavy task that needs a whole 24 milliseconds of CPU time. And right behind it, you've got P2 and P3, 2 super quick, nimble tasks that only need 3 milliseconds each. So what happens when the big guy gets to the front of the line first? Well, you can see it right here. P1 grabs the CPU and doesn't let go for its entire 24 millisecond run. And the whole time, our 2 little processes, P2 and P3, are just stuck. They're sitting in line, twiddling their thumbs, completely blocked until P1 is good and done. And the results of that? The average waiting time for a process is a whopping 17 milliseconds. Now, you can't really say it's unfair. Everyone waited their proper turn, but efficient? Not even close. You can just feel the wasted time. But this leads to a really interesting thought. What if the order was just different? What if by sheer luck our 2 little fast jobs showed up just a moment before the big one? Does that little change really matter all that much? Oh, it matters more than you can imagine. Look at this. P2 zips through. P3 zips through. Boom, boom. They're both done in just 6 milliseconds total. Yeah, the big P1 still has to wait its turn, but those 2 short jobs got in and out in a flash. The whole system just feels faster, more responsive. And the numbers back it up completely. The average wait time plummets from 17 milliseconds all the way down to just 3. This proves a huge fundamental flaw. With first come, first served, your entire system's performance is basically held hostage by random chance. This problem actually has a name. It's called the convoy effect, and it's the perfect name for it, right? It's exactly like being stuck behind a slow-moving truck on a 1-lane road. That one long process creates a massive traffic jam for all the smaller, faster ones, and the whole system just grinds to a crawl. So, to beat this convoy effect, we need to be smarter. We need a new strategy. Enter shortest job first, or SJF. Instead of just blindly taking the next in line, the scheduler actually looks at all the waiting jobs and says, okay, who's the quickest? And picks that one. It's like an ER doc deciding to handle the guy who needs 3 stitches before the person who needs a 6-hour surgery. Now, here's the wild part. Shortest job first is, and I'm not kidding, provably optimal. For any group of processes you can imagine, this method will always give you the absolute lowest possible average waiting time. It's perfect, right? Well, you knew there had to be a catch. And here it is. It's a big one. For shortest job first to work, the operating system would need a crystal ball. It has to know, before a process even starts, exactly how long it's going to run. And it can't. That's impossible. Now, systems can try to guess based on past behavior, but at the end of the day, it's just that, a guess. So if we can't be perfectly efficient because we can't predict the future, maybe we're chasing the wrong goal. Maybe we should optimize for something else entirely, like fairness and responsiveness. And that brings us to a totally different way of thinking, an algorithm called round robin. This really lays out the 2 philosophies. SJF is all about minimizing the total waiting time, how long you're stuck in the queue. But round robin, it's all about minimizing response time, how long it takes for a process to get started and give you some kind of feedback. It's not about finishing the fastest, it's about making sure nobody feels ignored for too long. So here's how it works. It's like taking turns. Every process gets a tiny little slice of CPU time. We call it a time quantum, maybe 1/100th of a second. If your time's up and you're not done, a timer goes off, the OS yanks you off the CPU. That's called preemption, and you go to the back of the line to wait for your next turn. Let's go back to our old friends P1, P2, and P3 and see what happens. P1 runs for its little 4-millisecond slice, but then bam, its time is up. P2 gets a turn, and since it only needs 3 milliseconds, it finishes. Then P3 gets a turn, and it finishes too. Only then does P1 get another slice of time. That long job gets chopped up into pieces, letting our short jobs finish way, way earlier. The whole system feels snappy as heck.
Okay, so we've got one method that's super efficient but requires a crystal ball, and another that's super responsive but maybe not the fastest overall. So what do modern systems like Windows, macOS, or Linux actually do? Well, they don't just pick one. They do something brilliant. They combine the best of both worlds with a system called a multi-level feedback queue.
Here's how this ingenious system works. A new process arrives and gets put in the highest priority line, which uses round robin with a really short time slice. This is perfect for interactive stuff like your mouse cursor or typing. But if a process uses up its entire time slice, the system thinks, this might be a longer job, and it demotes it to a lower priority queue with a longer time slice. If it still keeps running, it gets demoted again, eventually landing in a bottom feeder queue that just slowly works through long jobs, first come, first served. And that's the absolute genius of it. The system automatically sorts jobs based on how they actually behave. It doesn't need to predict anything. The quick, interactive stuff you're actively using stays in the fast lanes, getting immediate attention. Meanwhile, the heavy background tasks, like a video encode or a big download, filter their way down to the slow lane, where they can chug along without ruining your experience. It really is the best of all worlds. So the next time your game starts to stutter while a big file is downloading in the background, you'll know exactly what's happening. You're feeling a real-time scheduling conflict. And it leaves you with a final thought. That scheduler is making these trade-offs for you constantly. But if you had the choice, what would you tell it to prioritize? A perfectly smooth, high frame rate in your game, or getting that download finished a little bit faster? There's no right answer, but it tells you a lot about what we value in computing.